Good day, everyone. We are Blackpink and we are here to discuss Unit 2, which is leveling. We will introduce you guys to what leveling is, as well as the definition of terms and the different kinds of leveling, which are differential leveling, profile leveling, reciprocal leveling, and double-rotted leveling. And to be discussed by yours truly, Diane Gloroterte, on what leveling is. So, leveling is the process of directly or indirectly measuring vertical distances to determine the elevation of points, or basically their differences in elevations. It is used in surveying to establish the elevation of a point relative to a datum, or to establish a point at a given elevation relative to a datum. For the definition of terms, we have the level surface, which is a curved surface that is perpendicular to the direction of gravity or the plumb line at any point. Next, we have the level line, which is a curving line on a level surface whose points are all normal to gravity's direction and equal distance from the Earth's center. Next, we have the horizontal surface, which is a plane that, at a given point, it's tangent to a level surface. At the same point, it is perpendicular to the plumb line. Then we have the horizontal line. It is a straight line in the horizontal plane that is at one point tangent to a level line. At the point of tangency, this line is perpendicular to gravity's direction. Next, we have the vertical line. It is a line that runs parallel to the direction of gravity at any point. The direction taken by a string supporting a hanging plumb bob passing through a point exemplifies it. Then we have the mean sea level. It is a hypothetical sea surface located halfway between high and low tides. It is used as the reference surface for the majority of ground elevations. So the geode in the picture is a model of the global mean sea level that is used to measure precise surface elevations. So the datum is any level surface that is coincident or parallel with the mean sea level and is used to refer to elevations in a specific area. When establishing relative altitudes over a small area, any surface can be used as a datum. So the elevation of a given point is the vertical distance above or below mean sea level, or any other specified datum. And lastly, we have the difference in elevation. It is the vertical distance between two level surfaces on which 2 points are located.
So hello everyone, I am Shane Mayor Takil and I'll be reporting about differential leveling. So first of all, let us know what is differential leveling. So differential leveling is a means of transferring elevations from a known elevation to an unknown elevation. So this unknown elevation is usually can be found in benchmarks. So it is the process of finding the difference in elevation between two or more points. So when the 2 points are within the sight limits of the instrument, 2 readings are taken. The difference in rod readings represent the difference in elevation between the 2 points. So it is actually a technique used to determine differences in elevation between points that are remote or far from each other. Since if it is far, it is not admissible or the instrument cannot precisely read what is on the rod since it is too far. And also there are some instances that the elevation in a specific point is higher than the height of the instrument, so it could block the line of sight of the instrument. That is why we make use of differential leveling. So differential leveling requires the use of a surveyor's level or an optical level together with graduated measuring rods. So before learning about the different steps and process of differential leveling, let us familiarize ourselves first with the terms that is used in this topic. So first is the benchmark. So benchmark is the known elevation or the assumed elevation that is commonly found on water hydrants or on bridges. So it is a fixed point of reference whose elevation is either known or assumed. They may be permanent or temporary. So it is a reference point that we make use whenever we do some differential leveling. So there are things that we call arbitrary benchmarks. So in small survey works or engineering projects, it is important to know the difference in elevation of 2 points. However, there are some cases that there is no benchmark within the area of the project. So when this happens, we cannot predict the exact reduced level of that area with respect to the mean sea level. So, some fixed points in that area are arbitrarily taken as benchmarks and values are assumed. The assumed arbitrary benchmark values may be 50 meters, 100 meters, 200 meters, etc. So next is the backside. So backside is a reading of a known elevation. It is a measurement that is taken on the top of a known elevation. So next is the foresight. Foresight is the opposite of backside. It is a reading of the unknown elevation. So it is a reading of or measurement taken in a specific point that in which the elevation is not yet known. So next is the height of the instrument. So from the word itself, it is the height of the instrument, but with respect to the level of sight or the line of sight on that specific instrument. So it can be calculated by adding the backside measurement and the elevation of that specific point. Next is the turning point. So it is an intermediate point between benchmarks which provides a temporary point of known elevation for a level circuit between two benchmarks that is a long distance apart. So let's say we have a benchmark and a rod placed on top of that benchmark. A distance away from that benchmark and a rod is the instrument. So on the other side of the instrument, we place another rod. So that specific point in which we place a rod on that point, we call that turning point. So lastly is the backside distance and the foresight distance. So these are the distances from which the center of the instrument to the rod on which a backside or foresight is taken. So basically it is a distance from the instrument to the rod in which it is where we took a backside reading or a foresight reading. So we are now on knowing the steps or process for differential leveling. But before diving into that, we have to know first the formula that can be utilized later on. So first is the height of the instrument. So the height of the instrument can be calculated by adding the elevation of that specific point and the backside reading of that specific point. Next is the elevation. So to calculate elevation, we just have to subtract the foresight reading from the HI or height of the instrument. So let us now move on to the steps for differential leveling. So number one is we have to locate, benchmark, or find a point of known or assumed elevation. In our example here, our benchmark is in PM35. So since it is a benchmark, we already know the elevation of this point. So we have an elevation of 154.375. So next, we place a rod on top of that benchmark. So this line here is the rod. So next is we set up the instrument, which is a distance away from that rod. So we have an instrument here at station A. We then take a backside reading. So we call it a backside reading since the elevation here is known. So we have a backside reading of 1.255 and we have an elevation of 154.375. Since we have these two, we can now calculate for the height of the instrument. So we just add the elevation, which is 154.375, plus the backside reading, which is 1.255. We now have a height of the instrument, which is 155.630. So we already have an instrument height. Next is we place a rod on the other side of the instrument. So this will be our step 5. So we place a rod in this station 2. So this will be our turning point 1. So next, since we already placed a rod, we can now have a reading. So what do we call this reading since there is no known elevation yet in this station? So we call it a foresight reading. So we have a foresight reading of 1.100. So we have a foresight reading and we also have the instrument height. We can now calculate for the elevation in station 2. We just subtract 1.100 from 155.630. So we can use your calculators. And now we can have the elevation, which is 154.53 or 5.530 in 3 decimal places. So next is move the instrument and set up again. So we move the instrument here in station B. Then we get a bauxite reading. So it is now called a bauxite reading since we already know the elevation for station 2. So we have a bauxite reading of 0.465. We then add this elevation in station 2 and the bauxite reading in this also specific point. We can have the instrument height. So 154.530 plus 0.465, we have 154.995. So this will be our new instrument height in station B. We then place a rod here for station 3 for us to take up a foresight reading. So it is a foresight reading because there is not yet known elevation here. So we get a foresight reading 2.095 and we already have the instrument height. So we can now have the calculation for this elevation here. So 154.995 minus 2.095, we have an elevation of 152.900. So next is we move the instrument again here. Then we take another bauxite reading and add that bauxite reading and the elevation to get the instrument height. So the process repeats until you get to your last station or your temporary benchmark. So that would be the process for differential leveling. Let us now make use of the simulator that I found in the internet. So before trying the simulator, let us now first look into the formula for arithmetic check. So this formula is essential to determine if you have some errors in your calculations while doing the differential leveling. So here we have elevation for benchmark 4 or the last benchmark is equivalent to the elevation of the first benchmark plus the summation of the bauxite readings minus the summation of the foresight readings. So we can now we can check that later in our simulation. So you can see here a simulation for differential leveling. So on the left side is a field notebook. So on this field notebook, we have some abbreviations and columns and rows. So for BS, meaning bauxite measurement, HI, instrument height, FS, foresight reading or measurement, LEV, elevation, desk, description, and for this station, we have BM for benchmark, TP for turning point. So turning point 1, 2, 3, 4, 5, and so on and so forth. On the bottom corner of the field notebook, we have a summation for the bauxite readings and the summation for foresight readings. So this will be utilized later on if we have our arithmetic check, whenever we have our arithmetic check. So this formula is familiar, right? So we are going to dive to that later on. So let us first go to the simulation. So the measuring rod is on the benchmark with a known elevation of 316.56. So we begin by taking a bauxite. So bauxite, since the elevation is already known. So the bauxite measures 4.09 feet. So using these values, we can now calculate for the instrument height. So we just add the elevation, which is 316.56, plus the bauxite reading, which is 4.09. So we have 320.65. So we type that here. Let's check if our answer is right. Correct. So now we can now move to turning point 1. So move rod. So the measuring rod has moved to turning point 1. So we now take a foresight reading since the elevation is not yet known. So we take a foresight. So we have a foresight of 9.52 feet. So using this, we can calculate for the elevation for this specific point or turning point 1. So 320, which is the instrument height, 0.65 minus 9.52. So 311.13. So this will be the elevation for turning point 1. 311.13. Check. Answer. Correct. We now then move the instrument. So since the elevation for turning point 1 is already known, we take backside. So 4.12. Again, we calculate for the instrument height. We just add 4.12 with the elevation, which is 311.13. So 315.25. Check answer. Correct. Now move the rod. So this will be the turning point 2. So take a foresight. Foresight because there's not yet known elevation. So foresight measures 9 feet, exactly 9 feet. So to calculate for the elevation, we just subtract it from the instrument height, which is 315.25 minus 9.00. 306.25. Let's check if it's right. Correct. We now move the instrument. Before moving on, notice the placement of the measurements. So for benchmark, we have here the elevation that is written on the same row with the benchmark. However, for the backside and instrument height, it is written on the row below that. So that should be the right placement for those values in order to have a neat and clean field note or field notebook for differential leveling. So for foresight and elevation, it is written on the turning point 1 since it was taken on the turning point 1 for the foresight and elevation. However, for the backside, it is still taken in turning point 1, but it is after na. So we have it is in the row next to that row of TP1. So back to the simulation. So the instrument has moved. We now take a backside reading. So 6.13 feet. Then calculate instrument height by adding 6.13 to the elevation, which is 306.35. So 312.38. Let's check if our answer is right. Correct. We now move the rod. So the measuring rod has moved to turning point 3. We now take a foresight reading. So foresight because there is no elevation that is known yet. Not yet. So foresight measures 2.07 feet. So we just subtract that from the instrument height, which is 312.38, in order to get the elevation of that point. So 310.31. 310. Let's check if our answer is right. So correct. We now move the instrument. So the process just repeats and repeats until you get to your last station. Now we have to sum up all of these backside readings as well as all of this the foresight readings. So if you were familiar with this equation, I discussed this earlier on the previous slide. So we are expecting to have an answer of that is similar to the last benchmark or the turning point 6 or TBM. So first let's summation of the backside reading. So 2.12 plus 6.13 plus 3.11 plus 3.20 plus 2.36. I hope I was So we have 23.01 check first 4.09, 4.12, 6.13, 3.11, 3.20, 2.36. So a total of 23.01. So for the foresight reading, we have 9.52 plus 9 plus 2.07 plus 6.50 plus 9.19 plus 7.92 for a total of 44.2. Let's check first the answer for the summation. Correct. So for the summation of foresight, 44.2. Let's check if our answer is right. Correct. Now for the arithmetic check, the BM elevation plus the summation of backsight readings minus the summation of the foresight readings should be equivalent to the TBM or the temporary benchmark. So our last station or our last point, which is 295.37 in elevation. So let's try calculating our BM elevation, which is 316.56 plus the summation of the backsight readings to 23.01 minus the summation of foresight readings 44.20. So 295.37. So similar to the TBM. So everything is right. Our field notes is right. Yay! Let's check. Ta-da! Correct. Now we are done with differential leveling. Thank you for listening. So here you can view the summary. Yay, we're done.
Hi everyone, I'm Andrea Silva and I'm going to talk about profile leveling. Profile leveling is the process of determining the difference in elevation along a fixed line at designated short measured intervals. It provides data from which a vertical section of the ground surface can be plotted. In profile leveling, intermediate foresights are taken where necessary to accurately portray the existing ground surface along the route surveyed. A profile is then necessary for the design and construction of roads, railroads, canals, culverts, bridges, sewer lines, etc. So let us define some terms used in profile leveling. First, we have the profile, a curved line which graphically portrays the intersection of a vertical plane with the surface of the Earth and the horizontal distances between the points along a surveyed line. Next is vertical exaggeration, which is drawing the vertical scale for a profile much larger than horizontal scale to accentuate differences in elevation. And then we have intermediate foresights, taken along the center line of the proposed project to provide accurate representation of the ground surface. They are also called ground rod readings. In profile leveling, we also have stationing, a numerical designation given in terms of horizontal distance any point along a profile line away from the starting point. In the figure, the distance between the horizontal line AB is divided into 15 stations, where point A is the starting point and point B is the ending point. There are two kinds of stations, full stations and plus stations. Full stations are points established along the profile level route at uniformly measured distances. They are usually multiples of 150, 30, 20, or 10 meters. In the figure, we can see that there are 9 full stations which are 10 meters apart. On the other hand, a plus station is any intermediate point established along a profile level mostly for the location of critical points, such as the intended location of culverts and bridges. We can see in the figure that the station designated as X is a plus station, since it is not uniformly distanced from the rest. It is also the lowest point from the profile, which can be concluded that plus station X is located at a critical point. Procedure for profile leveling. The profile leveling survey party consists of the route survey party and the leveling survey party. The route survey party assigns full stations and finds the centerline of the route. Here we have 11 full stations, 10 meters apart. The leveling survey party then finds a convenient location for the instrument and sets it up. After leveling the instrument on the location, they take the backsight reading on the benchmark, which has a known elevation. After backsighting the benchmark, they can now proceed to take the intermediate foresight of the first station. If there is no obstruction from the side of instrument, they can directly take the intermediate foresight of the second station and the next and the next. But for example, there is an obstruction of sight in the fifth station, such as a tree, the rodman establishes a turning point, which is an intervening point to proceed to the next instrument location. After establishing a turning point, the instrument will not be moved yet as the foresight of the turning point is still taken. Now after foresighting the turning point, the instrument is then moved to a convenient location where it can sight more stations. Again, set up and level the instrument, then take the backsight of the turning point. Consequently, the intermediate foresight readings will proceed onto the next stations. If again there is an obstruction of sight in the next station, the next turning point will be established. Take the foresight of the turning point and move the instrument. Then backsight the turning point. Finally, proceed to take the intermediate foresights until the last station. That is the end of the profile leveling procedure. A quick note on the main difference between profile and differential leveling is the number of foresights taken from each setup or location of the instrument. While differential leveling needs to move the instrument after every foresight reading, profile leveling does not do so, given that all stations are visible from the instrument or that there are no obstructions found in the area. We then proceed to the calculations. Here we have a sample profile leveling illustrative problem. Initially, given the backsight and elevation of the benchmark, we compute the height of the instrument using the formula elevation plus backsight. That is 125.5 plus 0.95, which gives us 126.45 as the HI. Next, we can calculate the elevations among all stations with the formula height of the instrument minus intermediate foresight. And for the turning points, height of the instrument minus foresight. For the first two stations, we perform HI minus IFS. And for the first turning point, we perform HI minus FS. To get the new height of the instrument, we add elevation plus the backsight. Then continue with the new height of the instrument, subtract to the following IFS. Get the new height again and subtract with the following IFS of the following stations. Repeat the formulas until the last station. We also get the summation of the backsight and summation of the foresight for the arithmetic check. Now we have completed the elevations on all stations, benchmarks, and turning points. We have also calculated for the 5 heights of instrument. We then proceed to After doing the calculations, we perform the arithmetic check. It is found by the formula elevation of benchmark B is equal to the elevation of benchmark A plus summation of backsight minus summation of foresight. Substitute the given values. Elevation at benchmark B is 124.13, Elevation at benchmark A is 125.5, summation of backside is 8.41, and summation of foresight is 9.78. We can see that both sides are equal to each other and therefore no error is made while doing the profile leveling and its calculations. Lastly, we construct a profile of the ground by placing the stations at the x-axis and the elevations at the y-axis. Take note that the turning points and benchmarks are not placed at the x-axis since they are not part of the centerline of the route. Then, plot the points according to the data and connect using a curved line. This is now the profile of the ground. This profile made is then useful for projects such as roadways to compute the volume of fill and volume of excavation in areas with big differences in elevation. That is all for profile leveling, and next we proceed to reciprocal leveling to be discussed by Dwinpearl. Thank you.
Hello everyone, I'm Dwinpearl Villarino and I'll be talking about Unit 2.4, which is about reciprocal leveling. So before anything else, I would like to point out that leveling can actually be spelled with one L or two L's, so both are actually correct. So to start, reciprocal leveling is a surveying method between 2 points at far distances where height measurements are taken at both directions to eliminate the effects of possible atmospheric refraction and the Earth's curvature errors. At far distances, the Earth's curvature and atmospheric reaction can cause significant leveling calculation errors more so than at short distances. Reciprocal leveling is common for measuring the distances between 2 points in rivers, lakes, and rugged terrains. Atmospheric refraction is defined as the change in the direction of propagation of electromagnetic radiation or sound waves in traversing the atmosphere. In simpler terms, atmospheric refraction changes the direction of light, causing a distant object to appear higher than the actual position. So this phenomenon occurs because the higher the altitude, the lower the density of the air. So this is why we perform reciprocal leveling so that we can eliminate the changes or the errors made by atmospheric refraction. So when solving for the measurements, the error should be identical when measuring from either side. So we simply need to calculate the difference between the two pairs of points. Now, how do you perform reciprocal leveling? So, for example, please refer to the image being projected right now. For this situation, we have point A on one side of a canyon, which is to the left of your screen, and point B on the other side of the canyon, which is to the right of your screen. To start, our benchmark or point of reference is located in A. We position our surveying device on the ground close to point A and measure its distance from the ground. This is our small letter A. We perform 4 trials for the sake of accuracy. We label this as BS or backside. From the same position, we measure point B's distance from the ground. We label this as FS or foresight and take 4 trials as well. We calculate the sum for each BS and FS and then get the means of both BS and FS. The difference in elevation or DE sub 1 for station A can be calculated by subtracting B from A as seen on the screen, so we get 1.285 minus 0.676, which is equal to 0.609. We do the same process again, but this time we make our benchmark or point of reference located in B. So this time, instead of small letters A and B, we have A prime and B prime respectively to emphasize the distinction between the two. We perform 4 trials as well for both BS and FS, calculate the sum, and eventually the means of each ES and FS. So just like previously, in order to get the difference in elevation or DE sub 2, we subtract B prime from A prime as seen on the screen, so we get 2.143 minus 1.478, which is then equal to 0.665. By calculating the total of these two pairs of measurements and dividing it by 2 to get the average, so in other words, DE sub 1 plus DE sub 2 and the whole equation divided by 2, we can determine what the leveling error is to arrive at what a true level line would be. So therefore, the answer is 0.637.
Hello, and once again, this is Diane, and now we are here to talk about double-rated leveling. So, double-rated leveling is a method of determining differences in elevation between points by employing two level routes simultaneously. So, double-rated leveling is just like its name. It's just like differential leveling, but there are two rods. At each setup of the leveling instrument, two sets of independent backsides and foresides are taken. And this method has an advantage of providing a continuous check on the process of determining ground elevations while the work is in process. Here we have a schematic diagram of double-rated leveling. So, in the diagram we are given a BM1 elevation, and the yellow setup there with crosshairs are our instrument setups. And as you've observed, there is TP1H and TP1L, TP2H and TP2L, and etc. The H and L there just represent our two rods. And the green values represent our backsides, while the red represent our foresides. And from the diagram, we have an unknown BM2 elevation. To solve for the unknown BM2 elevation, we have to compute for the double-rated levels. As you can see in the table, there are two duplicated values for BM1, and it's just duplicated for consistency with the rest of the values in the table. To solve for the missing height or the HI of BM1, we simply just have to add the elevation and the backsides. To solve for the values of TP1H, first we have to input the foresides. And to find the elevation, we use the height from BM1 and minus it from the foresides. Third, we input the value of backsides of TP1H. Then fourth, we can solve then for the height of TP1H by using the new elevation plus the backsides. And we use the same calculations for TP1L, TP2H, and so on and so forth until we arrive at the elevation for BM2. Once again, there are two duplicated values for the foresides of BM2 because it is for consistency. But there are two different values for the BM2 elevation because of our calculations. Since we are given two different values for the elevation of BM2, we have to compute the average. And computing the average of these values would be 202.875. We also have to perform the arithmetic check for our values, which is DE1 equals to the absolute value of the summation of all our backsides minus the summation of all our foresides divided by 2, whereas DE2 is equal to the elevation of BM1 minus the mean elevation of BM2. And this DE1 and DE2 must both be equal. And now we solve for these formulas using our computed values. The sum of all our backsides is 12.975, and the sum of all our foresides is 18.323, while our given elevation of BM1 from the previous slide is 205.549. Then we have to substitute these values to our DE1 and DE2. For DE1, we have the absolute value of 12.975, the sum of all our backsides, minus 18.323, the sum of all our foresides, divided by 2, which is equal to 2.674. Next, solving for DE2 is our elevation BM1 205.549 minus our mean elevation of BM2, 202.875, and this is equal to 2.674. As you can see, our values for DE1 and DE2 are both equal, which means that we have done our arithmetic correctly. And that's all for double-rotted leveling. Thank you for listening, and we hope you have learned something from our report.